Okay, everyone, welcome back to Legion School. Apologize for missing last Wednesday, but we are back and ready to go today. So today, I think we are ready to start looking at the logical dependence analysis process inside the region tree, which is actually one of the more interesting parts of Legion. We effectively managed to get through a bunch of infrastructure, which allows us to understand we got through all the infrastructure necessary for understanding what's gonna be going on here today. And so today we'll actually start looking at how we could do logical dependence analysis. And then on Wednesday, Sean will be back here to talk some more about the low-level runtime. Okay, so let's start off today. We're going to go look at a couple places of code where we already saw logical dependence analysis was invoked, and we're going to see that the same function was used in many different places. And then we'll go dig inside that function and actually see what happens. So you recall that when we were looking at, let's jump into legionops.cc here. You recall that when we were looking at all the different kinds of legion ops that we saw, we had a particular method in the pipeline called trigger dependence analysis that was invoked at the very beginning of the pipeline for all the different kinds of operations that were being done inside of the Legion runtime. So here we're looking at map-op trigger dependence analysis. And you see we do our begin analysis and end dependence analysis call. We looked at those in pretty good detail. And what we saw before was we saw this method here to perform dependence analysis being performed on the region tree forest, asking it to perform the dependence analysis for the region requirement that I'm highlighting right here that this map-op has. And so this, the idea of this call was to actually register dependencies on this mapping operation based on the operations that came before it. So effectively, we're going to do a dependence analysis to figure out what this map op might have dependencies on from previous operations within the same context. And that's what this perform dependence analysis call is actually doing. If we continue looking at trigger dependence analysis, here's the one for copy ops, you'll see that we're using the same call, perform dependence analysis. And again, we're passing in a particular region requirement for this particular copy op. Notice that this is in a loop. We can loop over the source requirements and we loop over the destination requirements, and both loops end up invoking perform dependence analysis and passing in a region requirement saying exactly which region requirement we want to do this dependence analysis for this particular operation. And of course, if I keep going down here, see if there are any other, I guess, yeah, here's another interesting one where we call perform dependence analysis. These are close ops. Again, we're calling perform dependence analysis on this particular close op. And it turns out that if I go back to Legion tasks.cc and we're to look at trigger dependence analysis for both individual tasks, so here's the individual tasks. Again, we see a loop here. Over all the regions that this task has requested privileges on via region requirements. And again, we see a call to perform dependence analysis, again, passing in a region requirement for which we're going to do this dependence analysis. And that was for individual tasks. And if we also look at index tasks, we will see exactly the same thing right here with this loop right here. Okay, so what we want to do today is actually dig into this perform dependence analysis call and actually see in a little more detail what it's doing, because we can actually now look inside the region tree forest and see the kind of analysis that it's doing in order to compute all of the dependencies that came that this operation should have on all the operations that came before it. Okay, so let's go find perform dependence analysis. It's going to be in regiontree.cc. Obviously, as I mentioned before, every time we invoke a method on the region tree forest, it will always go through the region tree forest interface. So I'm jumping into regiontree.cc here, waiting for GitHub. And let's see, we call perform dependence analysis. Okay, oh, I went a little too far. Jump back up to the top here. Here we go. Okay, so here's the perform dependence analysis function. It's actually pretty simple, because what it's going to do is actually just dispatch the actual dependence analysis. So let me give you a little bit of a preview of what is going to happen here at a high level, and then we'll dig into some of the code to actually see what's going on at a lower level. Okay, so the idea behind the dependence analysis in Legion is that for every one of the region trees that a parent task has privileges on, we're going to keep some state. And again, we talked about context. So what we're going to do is we're going to keep a context for that parent task. And for all the region trees on which that parent task has privileges, we're going to register the operations in these region trees in order to keep track of which ones are still outstanding and capable of, or which we're going to register all the operations wherever they're going to need to use a region inside of these region tree forests. And then as later operations get launched, what we're going to do is come along and actually try to figure out where there are dependencies from the previous operations that came along that were registered based on the regions that they're actually accessing. Okay, so how is this going to work? So what we want to do is actually find all of what we call the interfering operations based on this region requirement that we're looking for dependencies on. So in order to do this, what we're going to do is we're going to do what we call a region tree traversal. And the idea is that we're going to traverse from where the parent task originally, for whatever region that we're looking for in this particular region requirement here, we're going to traverse a path, and you can see we're getting passed into region tree path here, and I'll talk about what that means in a minute. We're going to traverse a path from where the parent task had privileges on a region down to where this child operation is requesting privileges on this region. And as part of this traversal, what we're going to do is find all of the other operations that were registered along this path and are therefore potentially interfering with this particular operation. And then we can register dependencies on all of those other operations. And so this is going to give us a very concise way of figuring out exactly which operations that were launched before us we should have dependencies on based on this region requirement that we're analyzing here. So this path here, and let's see, I'll probably skip showing you how this gets computed today. It's actually very simple. But effectively what this path describes is it's a path through the region tree from the parent node where the parent task had privileges on a region down to where the child task is requesting privileges on this region requirement. And, we've looked at some of the region tree details, and really what this path is just a vector of colors through the region tree forest. And it says, at every node, which child tree which child node of this particular node in the region tree forest. So it's really just a vector of colors that gives us a path through this region tree forest. So I'm not going to dig into detail on this region tree path. It's actually pretty dumb. But really, it's just a way to define which subnodes to take as you traverse down through this region tree. Okay, so let's actually see how we do this dependence analysis. As I told you, we're going to do this traversal. So the first thing that we're going to do is we're going to get the parent node where the parent task has privileges. So one of the things that happens when you create a region requirement in a Legion application is you also have to specify the parent region for where this operation is going to derive its privileges. And so the first thing that we can do is we can actually get the parent node from the region requirement. So we can see we're taking this parent logical region from this requirement, and we're getting the node for the parent node wherever we're going to start our traversal from. The next thing we're going to do is we're going to compute what we call the user mask, which is the set of fields which this region requirement is going to be requesting privileges on. And what this is going to give us another way of detecting interference between different operations that have already been registered. Effectively, this field mask is a compressed representation of this set of privileged fields. They allow us to know exactly which fields we're going to be accessing and to test them against other users very, very efficiently. And what this is going to allow us to do is figure out another way in which we can prove non-interference of operations, cases where we don't need to register dependencies on other operations. So even though two tasks might be using the same region, they might not necessarily be interfering if they're using different fields on that region. Field mask is going to give us a way of testing that to figure out exactly whether or not we're interfering on fields or not. Okay. And when we're done, the thing that we're going to register inside of the region tree forest to mark that we've effectively started using this region is one of these logical user structures. Logical user structures are very, very simple. They contain a little bit of information. They contain this operation, which is our self, since we're going to be registering our self inside of the region tree forest. It records the index of this region requirement for this particular operation. So for example, for map ops, this would always be 0. But for like a task, this is the index of the region requirement that we're registering. The region usage is going to carry the information such as the privileges and coherence and any reduction ops that are associated with this particular region requirement. So you can see it's initialized based on the region requirement. It doesn't actually store nearly as much state as the region requirement. It's a very simplified version. Effectively, it's just storing privileges and coherence and reduction ops. And then finally, we track our user mask, which is the set of fields which we're going to be accessing. You'll notice that, the thing that we want to avoid doing is we want to avoid storing fields in the form of STL sets and stuff because they're very expensive. And so these field masks end up being much more efficient. And so you'll see that the region tree does everything in terms of field masks for representing fields instead of using large sets of STL stuff. We'll probably see some of this tracing info stuff. This is for an optimization that we do for actually trying to memorize a lot of the results for this logical dependence analysis, and we'll definitely talk about this at a later stage. But you see, we're just capturing information about our operation. Okay, once we've set up all of these different things, what we can do is actually begin our traversal of the region tree to actually perform our analysis. And it turns out we do this with a single call. So we're going to call this register logical node function. Notice that we're going to pass in a couple different things. First thing we're going to pass in is the context. And so this is the context that our parent task has. Notice it gets passed in here from perform dependence analysis. And you'll remember this context is really just an integer that the parent task is allocated and uses for indexing into the logical states of the region tree nodes. So this context ID is just getting that integer and passing it in. We're passing in our user. This is the logical user structure that we just made right here. So we're going to pass this by reference. We're going to pass in the path, which is going to help us know how to traverse the region tree so that we can actually understand how to move from one node down through the tree to the point where we're actually requesting privileges. And then we're also going to pass in our tracing info. Okay. So let's actually dig in and go dive into this register logical node. Just to sort of forecast, once we're done this traversal, we are pretty much done. There's some extra special code here for handling restricted region requirements in the case of simultaneous coherence. I won't be getting into that today. You'll see there's a bunch of logging, but that's really it. So all the heavy lifting is going to be done by this register logical node function so that we can actually figure out who we have dependencies on. Okay, so let's actually go look at register logical node. Okay, so you'll see that register logical node, the first thing to notice is that this is a method on a region tree node. So you'll notice that this method is not specific being either a logical region or a logical partition. It could be either. Effectively, it's abstracted enough that it doesn't have to depend on knowing whether or not this is a region or a partition that we're traversing. And this is good because, different tasks can request privileges on both logical regions as well as logical partitions. So in the case of index-based launches, oftentimes we have projection region requirements which, request privileges on a logical partition and not on a logical region. And so that might end up being the end point. But the idea is that this method will allow us to traverse this path from where the parent task had privileges down to where this operation is requesting privileges, and to do so in a way that doesn't need to be specific to any one kind of region tree node. Okay, so let's actually see a little bit what's going on here. And actually, before we dig into some of these details of all the middle things that are going on here, what I want to actually show you is how this traversal actually works. So think of this, first off, as there's a whole bunch of code here that decides what we're going to do for this particular node. But down here at the bottom, there's a little case here. Actually, let me show you where one of the first things that we do is whether we want to figure out whether or not we've arrived at our destination node. So I'll show you the recursive case first, and then we'll dig into what we do on every single node regardless. So one of the things we do is we figure out whether or not we've arrived at our destination. So one of the things that we know is the depth of this particular region tree node in the region tree forest. And the path actually knows how deep it can go for when it's actually doing these traversals. So we can know whether or not we've arrived at our destination by asking our path whether or not it has a child for this particular depth that this region tree node is living at inside of the region tree. So based on this Boolean arrived value, you'll see two different cases down here. We have one case if we've arrived at our destination node, and we'll do some stuff here, and I'll go into this in some detail a little later. And then there's also the case where we're not quite there yet, where we still need to continue our traversal. And so what you see is that if we have the thing that we're going to do is we're going to get our next child. So you can see this is just grabbing the next color for our next child from this path operation, this path object that we have. We can then get the child, the region tree node that corresponds to the child for this particular color that was in our path. And then what we can do is we can recursively call register logical node on that child tree. And that's going to allow us to continue this traversal. So this is the recursive case. This is how we're going to walk down the path from where our parent task requested privileges down to where we are actually requesting privileges for this particular operation for us to find all of our dependencies. There's a special case here. I'll just comment on it briefly. There's a special case where we can know that effectively all of the path from where from where we are now to where we're actually going to request privileges isn't going to have any other operations to register dependencies on. And so in that case, we do a special optimization to do what we call opening, where we just have to open up a region tree without actually doing a whole bunch of dependence analysis and stuff. And that's a special case, and we'll see how we get this open-only code in just a little bit. But the general case is that we can just recursively call register a logical node, which is the method we're in right now, and that'll just traverse us down the tree from where our parent task have privileges down to where we are requesting privileges. Okay, so that's the recursive case. Let's actually see what we do on all of these inside of a node to actually do this dependence analysis to figure out who we're going to have dependencies on. Okay, this is actually probably one of the most important parts of one of the more important functions in Legion because pretty much the correctness of all of Legion depends on this one function right here. If we don't get this dependence analysis correct, the world tends to end pretty quickly in very, very bad ways. And so it's very important that we compute, a very precise set of we need to be correct to have dependencies on. Our analysis needs to be sound, but we also don't want to register a whole bunch of spurious dependencies. So we have to do both a precise and fast and sound analysis for computing dependencies. Okay, so you'll notice that there's lots of comments in this code, and that's intentional because this code is very detailed about what it's doing, and it looks very short. What you're going to see is that there's a lot of detail here and a lot of information that's moving around in order to do this dependence analysis correctly. So let's go everything at a high level, and then we'll probably dig into some of these details, dig into some of the details of some of these methods that we call in more detail. Okay, the first thing that we're going to do when we arrive at a node is we're going to check to see if there are any other subtrees, which are what we call open, effectively have other operations that have registered themselves in, which we need to do what we call a close operation. And the idea here is that we're traversing one particular path from where our parent task had privileges down to where we're requesting privileges. But it's possible that there are other operations which are using different regions that are not in this path, which may be interfering with us, in which case we need to go close up those region trees and compute dependencies on all of those operations so that we can get the right set of mapping dependencies and then be able to open up the path that we want to take. So if there are other parts of the subtree that are open, then we need to close them up so that we can traverse down the path that we want to go down. So what this close operation is going to do is it's actually going to perform the necessary close operations from the current node that we're at in order for us to continue our traversal. So we make one of these logical closer objects. It's going to be sort of our helper object for doing these various close operations. And what we're going to do is we're going to call this method siphon logical children. And what it's going to do is the siphon is going to perform the close operations only for the children which are necessary to be closed up based on this operation that we're going to be registering. You know, we're not arbitrary in what we close up. We don't just close up everything by default. We only close things that are necessary to be closed based on this operation that we're registering. So that's what this siphon logical children method is going to do. It's going to siphon off and close up the children which are necessary to be closed, but not any of the other ones. And so we'll actually go look at this siphon logical children method. It's actually pretty complex, but we'll dig into it a little bit more detail. You'll notice that the closer gets passed in here to actually be used as the basis for performing any close operations that need to be done as part of this siphon operation. Okay, after we're done with this operation, by the way, you'll notice that this siphon operation returns this Boolean open only, which we saw down here, which tells us whether or not any children are open, or whether or not we can safely do the open only optimization. So effectively, the siphon logical children case will tell us whether or not we closed up all the children, and therefore we can just and our previous and the child that we want to take is actually already closed, and therefore we can just do an open. Otherwise, we need to continue our traversal. So the siphon logical children call is what will set that open only, and we'll see how it does that a little bit later. Okay, after we've done all of our close operations to close up any subtrees which may be interfering with us, what we want to do is actually have our closer register all the operations that it closed up locally with this particular node. So what we do is we check to see whether or not it has what we call any closed fields. And effectively what this says is, were there any fields across any of the fields that we're traversing for this particular user that we had to close up across any of our children? I'm actually going to skip this. Let's actually see. Okay, I'll actually say what this does, and then we'll go on to the interesting parts of what we do after this. So let's say that we did have some closed fields. That means that we had at least one that closed up for each one of these closed field objects, in which case we need to actually register the close operations that we're going to perform here at this particular node of the region tree forest. There's a little operation here to figure out whether or not we have a next child, if we still need to be doing some of the traversal. What we're going to do is we're going to initialize all the close operations that this closer is tracking. And so what you'll see is that there could actually potentially be multiple close operations. So we might have had to close up different children for different fields inside of our subtree. And so there may be more than one close operation here, but effectively we can tell our closer to generate all of the close operations that we're going to need to do. The next thing we need to do is actually have all those close operations perform their dependence analysis. So the idea here is that we're going to create a bunch of different close operations, which are going to actually be responsible for closing up the physical region tree when they run. And they need to register dependencies on all the things that that are necessary for them that they might be interfering with. And then later, we're going to register dependencies on those close operations so that we know that those close operations will always be done before this operation that we're registering. So this is a very subtle point, and we're actually going to see that this perform dependence analysis on these different close operations is actually kind of tricky, and I actually just found a bug in it last week that we just fixed. So it's a very tricky thing to do here because we're actually effectively generating new close operations as the part of registering this particular operation in the logical region tree. And so getting their dependencies registered correctly is actually kind of tricky. But that's what this method here is going to do. It's going to register all the dependencies for those close operations that we just made. The next thing that we're going to do is we're going to get a mask all the different fields that we've closed up as part of this close operation. What we're going to do is actually understanding this is actually best done after we've described this part down here. So I'm going to come back to this little part right here, and it'll make a lot more sense once I've explained this code that's actually just right here. Okay, so let me describe a little bit about the state that we track on these on each logical node, and then we'll understand a little more detail what these registrations and filterings are doing here. Okay, before we describe what this code does, I actually want to jump back and show you what the logical state of a region tree actually looks like, so we can talk in a little bit of detail about what some of these data structures are doing, and then we'll understand what this code is going to be doing. So let me jump back here to regiontree.h. If I search for struct logical state, okay, so here's our logical state data structure. And you'll notice that it's pretty simple. Effectively, there are a couple of things that we have here. The first thing that we have here in this data structure, and by the way, just to refresh your memory, we have for every one of our region tree nodes, we have a set of logical states and a set of physical states that get indexed by the context that we're operating over. So you can think of this logical state as a data structure which stores the state of a context on a particular region tree node. Okay, and so we have a couple of different things here. The first thing that we have here is a set of what we call field states. These are the states of all of our child nodes inside of our region tree, and so we'll actually go look at what the field state data structure stores. But for right now, you can just think of it as tracking whether or not a child is open, and if it is open, which fields it's open for, and in what mode they're open in. Are they open in read-only mode, read-write mode, that kind of detail. So that's what all these different field states are in, or this field states data structure is storing. And then we have two lists here. Notice that both of them are lists of logical users, and we've already seen logical users today. Remember that we're actually trying to register a logical user as part of this dependence analysis. Okay, so we're going to have two lists of logical users, and we call them the current epoch users. So that's what this current epoch users are, and we have the previous epoch users. So let me sort of define what these current and previous epoch users are trying to capture. So in some cases, what we're going to have is that just imagine a case with a single field. Let's imagine our our logical region tree has only one field. Just to make things a little bit simpler here. One of the things that we might want to do is we want to figure out all of the people, and for right now, let's actually think about a very simplified case where we actually only have a single logical region in our region tree, and so that we don't have any partitions or anything like that. So we have a single region with just a single field to make life very, very simple. Imagine a case where we want to compute dependencies based on all of the operations that came before us. Well, we know that one of the tricks that we can do is we actually don't need to do analysis of everybody that came before us. We might only have to do analysis on a few people that came before us, because a few people before us, most likely register dependencies on all the people that came before them, effectively a transitive closure. So let me just give you a very simple example here. Let's say that we have, a task A that registers itself in a read-write mode. It's the first task that's launched, so it hasn't have anybody to detect any dependencies on, and we just say, okay, we're going to add that to the set of what we'll call the current epoch users. Okay, he'll be the current epoch, which effectively means the set of tasks which are currently using this logical region. Okay, the next thing we're going to do is we're going to register a task B, which is actually going to use the same region and the same field in read-only mode. In this case, we know that the task is going to obviously record a dependence on the previous operation because it's needing read-only, and the other guy had read-write privileges, and therefore he's going to need to have a dependence. And the idea here is that we can actually then move task A to the previous epoch users, and we're going to start a new epoch of users that it's going to be a read-only mode of epoch users. So that means that task A gets bumped down here to the set of previous epoch users, and task B becomes the new current epoch user. Now let's say we launch a task C, which is also going to use the region in read-only mode. Well, in that case, we know that he is not going to compute a dependence on task B because they're both in read-only mode. they can actually be running at the same time. So we can add it to the same set of current epic users as task B. So task B and C are now the current epic users, and task A is now the previous epic users. Okay, now let's say that we come along and we actually register a task D, which is again going to use the region in read-write with read-write privileges. So he's obviously going to have to register dependencies on both the current epic users because he's going to need to wait for them to finish reading before he can write. So he'll register dependencies on B and C and then become the new current epic, and we'll move B and C down to the set of previous epic users down here because they've now been relegated down to the previous epic users. And you might wonder, do you need to perform a dependency analysis between task D and task A? Because obviously, they're going to need to depend on each other. And the answer is, in this case, surprisingly, no. And the reason for that is we can actually bump task A out of the previous epic users because we knew that tasks B and C had already registered dependencies on task A. And anyone that came after the registered tasks dependencies on tasks B and C get a transitive dependence automatically on task A. So the idea behind these current and previous epic users is that we only need to remember back, about 2 generations of sets of users based on their privileges that they're using, whether they be read-only, read-write, or reduce. We only need to remember back effectively 2 phases in time for each field. And this allows us to actually keep track of a lot less information about the operations that are still going on inside of these logical states. And we're going to automatically get the necessary transitive dependencies on any operations that came before the set of previous epic users, so we don't need to worry about them. And therefore, we don't need to do a whole bunch of work to compute dependencies on them. And normally dependence analysis is a big O of n squared operation to do dependence checks against everybody that came before you. And really, this is a very effective way of avoiding that big O of n squared dependence operation on everyone that came before you. You can still get the big O of n squared case in sort of a worst case scenario. If you get a bunch of people doing read-only mode or something like that, you can end up doing a bunch of different checks that you don't really need to. But for most cases, it's actually very, very efficient to avoid doing dependence analysis against everyone that came before you. So that's what these current and previous epic users are tracking. And we're going to see it gets a little more complicated when we have multiple levels to our region tree as well as multiple fields. But in general, that's effectively what we're doing. We're keeping track of the set of current users and the previous epic users. And then for every operation that comes along, we're going to decide either to put it in the current epic or we're going to create a new epic and then bump everybody down one. So the current epic users become the previous epic users, and then the new task starts a new epic. Okay, so let's actually jump back to the code, and we'll actually see how this is going to happen. Okay, so I'm searching for register logical node. Okay, we're back here at register logical node. If I can keep my Mac in the right place. Here we go. Okay, so let's actually see what's going on here with this dependence analysis and see how we're actually going to update the current epic users and the set of previous epic users. Okay, so the first thing that we're going to do is when we have our logical user, we're going to do what we call we're going to do dependence checks against all the tasks in the set of current epic users. So that's what this perform dependence checks call is going to do here. And you'll see this is a very heavily parameterized function to actually do dependence analysis across all of the operations inside of the current epic users. You can see we're passing in our user that we're going to do dependence analysis on. We're also passing in the set of current epic users. We're passing in the field mask, which we want to do dependence analysis on. And we're also going to check whether or not there's actually a field here to say whether or not we've arrived at our destination. And we'll see how that gets used a little later. Okay, so what this is going to do, we're going to look at this method in detail a little bit later, but I'll describe it at a high level now. Perform dependence checks is going to iterate over all the current epic users and check to see if our current logical user has any dependencies on any of the users in the current epic list. And if it does, it's going to keep track of which fields the current epic user or the current user that we're registering has dominated. And when I say dominated, it means it registered a dependence on every single one of the fields inside of that current epic user. And what this is going to tell us is whether or not we're going to start a new epic for those particular fields of our logical user. And so that's what this dominator mask is indicating. Notice this dominator mask is a field mask, and it's reporting effectively which fields we should be starting a new epic for this particular user. And so what we want to do is, in the best case, actually determine that this user dominated all the different fields that it requested privileges on. And therefore, we can make it the new epic owner of all of those fields, and we don't have to do any dependence analysis against anyone in the set of previous epic users. However, if we were wrong and we actually concluded that, however, if we didn't actually dominate it, and we're actually going to join the current epic list for any one of our fields, then we actually need to perform dependence checks on the state of previous epic users. So what you can see here is we're actually doing a little bit of field mask math here. So we get our field mask here that's describing the set of fields which we dominated, which are the ones that we're going to start a new epic for. And then what we want to do is we want to figure out which fields we didn't dominate, so that we can actually do the additional dependence analysis on the set of previous epic users. So you can see we're using our first example of a field mask operator here. So we're taking the field mask for our user here, then all the fields that we're requesting privileges on, and we're subtracting out the fields that we know we dominated, and we're getting back a new field mask here, which says that this is the non-dominated mask. So these are the fields which we didn't dominate, and therefore we're going to be joining the current epic set of epic users for that particular field. And then if our non-dominated mask is not empty, so this double bang here, the first bang here is an operator on a field mask, which is returning a Boolean saying whether or not the field mask is empty. So if it's empty, this will return true. And if it's not empty, then it'll return false. And the second bang here is just the standard Boolean operator that's negating the result of that operation. So anytime you see this double bang on a field mask, all you're getting is the field mask checking to tell whether or not the field mask is not empty or not. So you see, if the field mask is not empty, our non-dominated mask is not empty, that means there were some fields for which we're going to current epic, and therefore we need to register dependence. We need to do our dependence analysis on the previous epic users for those particular fields. So you see, we don't need to pass in our full field mask anymore. We can just pass in this non-dominated mask. And so that's how we're going to do our dependence analysis. We're going to first check dependencies on all the current epic users. If there are any fields that we didn't dominate, then we're going to continue performing dependence analysis on those fields on the set of our previous epic users. Okay. So once we've done that, we've actually done all of the necessary dependence analysis at this particular level. And once we've done that, we've actually registered all the dependencies that we're going to need to for this particular operation. So effectively, we went through all the current epic users and all the previous epic users and found the ones that we depended on, and therefore we're able to register all of our dependencies. So these perform dependence checks will actually do the registration of our dependencies. Once we're done with that, we can actually do some special. We just have a little bit of an extra work to do if we're in the case where we actually arrived at our destination node. So if we've arrived at our destination node, there's actually a case where we can effectively do a couple of additional things here. The first thing that we can do is if we had any fields in our dominator mask, here's this double bang operator checking to see if it's not empty. So if any fields in our dominator mask, we can actually bump the privileges. We can effectively filter the current and previous epic users down for those particular fields. So you can see the first thing we can do is we can remove any users from the set of previous epic users based on the dominator mask. And what that will do is it will remove all any operations which we're still using those particular fields. And this is a nice optimization to do because effectively we've bumped the epic. We've started a new epic with our current user, so we can remove any one user or any one of the previous epic users because we're about to move the current epic down to be the previous epic for those fields. And so once we filtered out those out of the previous epic users, we can do a similar filter operation on the current epic users, which moves any users that interfere with this dominator mask from the set of current epic users down to the set of previous epic users. And so effectively, we're just bumping everyone down one phase for those particular fields that we dominated. Okay, and then once we're done with that, we're going to do the last important part of this operation, of this whole region tree traversal, which is we're going to actually register ourselves at this logical, as a user of this particular logical region node, logical region tree node. And the reason is that when people come along later, they're actually going to need to figure out that we're actually using this region tree. So what we do is we add our user to the set of current epic users. And that's going to make sure that anyone that comes along later is going to need to test against us for non-interference, or be able to register a mapping dependence against us. And so our logical user here that we're registering has all the information necessary to register a dependence on this particular operation. One important detail here, you notice that we're doing this call to add mapping reference on our operation. So we get the operation for this particular user, and we're adding a mapper reference, or mapping, what we call mapping reference. And the idea of this mapping reference is that even though an operation might run, and execute and actually even complete, it's not actually safe for us to recycle this operation quite yet, because some other operation might come along and need to register a dependence on it. So what you'll see is that we'll keep what we call mapping references. If there's anywhere that a operation is referenced inside of this logical region tree state, we have a mapping reference to that operation to make sure that it doesn't get recycled too early. And this is going to be important for resilience at a later point in time. But so that's all it's doing, is making sure this operation is going to get recycled, is going to complete and recycle before we're done registering all of our dependencies on it. Okay, and as I said, once we're done registering ourselves, then we're actually done with our traversal. So what I want to do now with the remaining time today is actually to dig into this perform dependence checks and actually go look at it in a little bit of detail. And what we'll do the next time is we'll actually dive into this siphon logical children call, because it's actually very, very important. And then at some point in a later date, we'll probably dig into this the closing operations to actually understand how they work in a little more detail. Okay, so let's actually go look at this perform dependence checks call so we can understand in a little more detail what's going on. And you just remember that we're using this it's sort of an overload. It's definitely a method that we invoke with lots of different parameters. And you see we're actually going to use it in more places than just these two. But for right now, you can see these are two calling sites. And in both cases, we're passing in different lists for doing our dependence analysis. Okay, so let's actually look at perform dependence checks. Okay, it gets called in lots of places. Here we go. Okay, so here's our call. It's templated on a couple different things. We'll see some details of this right now, but for most cases, this allocation type you see is just being used to track some of our memory usage for this Legion list data structure that gets passed in, which is the set of users which we're doing our dependence analysis against. So that's just a nice template parameter for making this easy to use. This has skip operation. We'll see where we need that a little bit later, but for right now, we're going to assume that this is false. There is no skip case for right now. Let's see. So here's our user, which we're doing, which is going to be the user that we're registering. And here's our set of previous users. So these are all the users that were registered in the tree previously, which we need to do our dependence analysis for. King mask, which is the mask for which we're going to be describing all the fields for which we're doing this dependence analysis on. And you'll notice that we have a special version of it. We're passing in this mask explicitly. We're not just using the mask that's stored in this logical user, because as we saw before, there are some cases where we actually only need to do the dependence analysis on a subset of the fields that are part of this user. So this check mask is describing which fields we're actually doing this analysis on. We get a little bool here saying whether or not to validate regions and so forth. And it's actually, we'll see a little bit later where we actually need that. Okay, so the first thing and the last thing that I'll point out is that you'll notice that this perform dependence checks call returns a field mask. And this is actually the set of fields which were dominated by this, the set of fields inside of this check mask that were dominated by this user. We did the traversal. And recall that the definition of domination is we dominate every single other user that was still using one of those fields. And therefore, we registered dependence on all of them. And if we did, then we can say that we still dominated those fields. OK, so we're going to start off. We keep track of, we store initially our dominator mask as our check mask. Another thing we're going to keep track of are the set of fields that we've observed, which are ones which we've registered at least one dependence on, or at least we've done at least one dependence check against. We don't actually have to register a dependence on it. We'll see why we need this observed mask a little bit later. OK, we actually do a little intersection test here to get what we call the user check mask, the intersecting set of fields for our user and for our check mask. We do some special stuff here for tracing. I'm going to ignore the tracing part for now. For right now, you can assume we're not tracing. OK, and now this part is actually exactly what you would expect us to do as part of our analysis. So we've actually made it down to sort of the leaf part of our dependence analysis here. What we want to do is try to figure out whether dependence on a previous logical user based on the usage of the region that was registered. We're going to iterate over all of these logical users, this list of logical users that we've registered before at this particular region. And we're going to check to see whether or not we need to register a dependence for our current user. OK, so the first thing that we can do is the first thing we're going to check is whether or not there are any overlapping fields. So you can see there's some more field mask math here. So we take our current user check mask. We're doing an intersection test. And we're doing an intersection test against the current field mask of this particular user that we're iterating over. And so we get a set back, this field mask back, which is what we call the overlap field mask, which says which fields we were overlapping for this particular logical user. And if there were any fields that were overlapping, then we need to continue doing our analysis. However, if there were no fields that were overlapping, we can actually jump all the way down here to the else case, which was actually, we'll skip the if case. And we're going to ignore the tracing part here. Let's see. We'll ignore this timeout thing for right now, but pretty much, what we end up doing is if we didn't have any fields that were overlapping, we're pretty much done. And we can go on to the next user. I'll describe this timeout case in just a minute. OK. So if we did have overlapping fields, then we need to continue doing our traversal to actually see whether or not we are interfering on in any other ways. Notice here we update our observed mask with the set of fields that we observed. So we can, this is the or equal operator. So it's doing a bitwise or across all the fields in the field masks to update the observed mask. So effectively, it says we saw a user inside of our set of previous user lists that we're using these fields. The next thing that we're going to do is we're actually going to do a check for whether or not these two users are interfering based on their privilege. So this check dependence type function here, notice it's taking in the region usage for both the current user or the previous user, as well as the user that we're trying to register, and it's going to return what we call a dependence type. And this dependence type says whether or not there are any dependencies between these two logical users based on their privileges. So notice there are a couple of cases here. There's the no dependence case, in which case we're done. And if that happens, what we're going to do is we're going to actually decrement this dominator mask because we saw a user which had some overlapping fields, but we didn't actually register dependencies on them, and therefore we can't, we can no longer consider one of those fields dominated. So we're going to update our dominator mask based on this the field mask for this particular user, in which case we can then break out of our switch statement here. The other cases are, there are anti-dependencies, atomic and simultaneous dependencies. We'll probably skip those for today. We can actually skip all three of these. But anti-dependence, you probably understand that's where you have a write after read case, where someone's going to be writing after another person is reading. And then we can also have a true dependence. This is where someone is reading after someone else has already wrote. Notice there's no break statement in this case, so this is just setting validate, and it's following through to this case. And if we do end up in this case, what we're going to do is we're actually going to try to perform the registration of this dependence. So with the remaining time, what I want to do is actually just show you what happens here when we do this register region dependence call, and hopefully I can also show you this. Actually, let me show you this check dependence type call, where that goes, because it's a very simple thing, and then we'll go see how this register region dependence call works. But you'll notice that this happens for any kind of dependence that's not a no dependence that's returned here. And then what we're going to do is, if we do have a dependence, we're going to take our current operation, and we're going to tell it to register a region dependence on the previous operation. So you see we pass in the previous operation, the generation of his operation, the ID, the index of his region requirement, and so forth, as well as some other information. So this register region dependence is actually going to register a mapping dependence from this operation on the previous operation. Okay, there's a few minutes left. I will just show you this check dependence type call just so you know where it is. And we'll look very briefly at this register region dependence call, and then that will be it for today. Okay, so let me jump back here. So this check dependence type call is actually in our utilities method, our utilities file. So we jump up here to legionutilities.h, and I search for check dependence type. What you'll see is that this method gets used a bunch. So we have pulled it into the utilities case. It's a static inline method. It's a pure function, so just based on these two region usage, figure out whether or not there are dependencies between them. So, if they're both, there are a couple cases here. If they're both read-only, then there's no dependencies effectively. There's a little special case here, but I'll skip it. If they're both reductions, if they have the same reduction op, then in most cases they're going to get a no dependence. But otherwise, if they're different reduction ops, there's going to be a true dependence. And then otherwise, down here we have all the special cases for at least one write. But somebody is writing. And then we have all the different cases for different coherence properties, whether or not things are exclusive, atomic, or simultaneous. And then we return the write dependencies for each of these different cases. So I'm not going to dig into the logic here. You guys can go through this yourself. It's mostly described in most of the Legion papers, what's going on here, based on which kinds of coherence interfere with each other and so forth. But it's pretty straightforward, and it's pretty much pure function calls. So I'm not going to dig into that in too much detail. But at least you know where this check dependence type is, and you have some clear idea of what's actually going on, looking at different privileges and coherence properties to figure out the various kinds of dependencies. Okay, I've got a few minutes left here. So the last thing that I wanted to show you was we were back in regiontree.cc here. And we were looking at perform dependence checks. Here we go. So we were looking at this this call here, which is where we're actually doing the registration of a dependence. So register region dependence. You'll notice that this is a call on a generic operation. And it's passing another operation on which it wants to register a dependence. So the place to find this, of course, is in legionops.h. Let's jump up here to legionops.h. If we search for register region dependence, here's the call on this particular on an operation, on the operation class. So if I scroll up here, you'll notice that we are on the class operation, which we have seen many times before. So this is a generic method that will work across all operations. It's a way that we register a mapping dependence between two operations, and it's generic, so it doesn't have to depend on any particular kind of operation that we're doing this on. So we can actually jump into legionops.cc. Let's see here. Once I can find it, here we go. We search for register region dependence. Okay, here's our register region dependence call. You can see it's actually not too complex. There's a little bit of stuff going on here. But the idea is that we want to actually register a mapping dependence between this operation and the operation that came before it. So this operation target. One of the first things that we do, just to show you how this method works very quickly at a high level, the first thing we do is check to see whether or not the operation is itself. This can happen because we can actually recycle operations inside of this region tree. And so therefore, it's actually not good. We actually have to handle a case where we've recycled a region tree operation, and it may try to register dependence on itself, but they're for different generations. And actually, this can actually happen in two cases. It can actually happen in a second case, which is they're the same generation, but they're actually the same different region requirements from the same operation. In that case, we do this report alias region requirements, which is going to report some undefined behavior for right now, but we'll figure out how to deal with that at a later point in time. In the other case, where they're not the same generation, then we can mostly just ignore this, unless we're tracing, in which case we actually want to do some recording. But in most cases, we just can return that, we didn't record a dependence because effectively we've advanced our generation. Okay, if we are going to do our registration, effectively do registration as true. It only gets set to false in some other weird cases, but for most parts it's true. We're going to tell our target, register a dependence on us, so effectively tell it who we are and that we're registering a dependence on it. It'll also tell us whether it'll update the number of outstanding mapping dependencies. You'll recall that this gets used for knowing when we've actually finished our dependence analysis stage. It'll also check to see whether or not we register any speculation dependencies. So these are good, both getting passed by value. These are integers for tracking the number of references. And this call will update them depending on if we register a dependence or not. And it'll also say, whether or not it's safe to prune this operation from the list, which can occur if the operation is already committed and continued execution. So you can see prune is the result, the Boolean result of this operation. But really, the main thing that we do is we try to perform this registration on this target operation. If we do succeed, if we actually register a dependence, notice registered dependence is this Boolean that's getting passed by reference in here. We initially set it to false, but if we registering a dependence, it gets set to true. If it does get set to true, this operation actually records it in a STL map, recording that we have an incoming, actually a mapping dependence on this particular target to make sure an incoming dependence on this target. Effectively, there's an edge in the operation dependence graph from that operation which needs to complete before we can actually start. So we have an incoming dependence on that target for this particular target generation. And if it validates a region, we'll talk about what that means at a later point in time. And then there's some extra code here for recording, tracing, and stuff like that. But the real key point here is that if we do succeed in registering dependence, we update or the count of this number of outstanding mapping dependencies. And at that point, we know that once this count goes to 0, we can actually finish our operation will actually be ready to map, and that's how we end up calling trigger mapping, which we saw at an earlier point in time when looking at operations. So if I actually search for outstanding mapping deps here, so I guess we'll look at how mapping dependencies get satisfied later, and then eventually at some point outstanding mapping depths, when it becomes 0, we can actually trigger our call trigger mapping, which is how we know that this operation can go on to the next phase. You can see that this is how we're tying back to the mapping dependence analysis that we saw for how operations actually get handled by the runtime earlier. So effectively, this dependence analysis is really wrapping back around to this operations stuff and actually allowing us to both register dependencies, and then once they get satisfied, we'll know that it's safe to actually map our operations. Okay, so I know that was a little rushed at the end. I'm sure we're going to go into some of this in some more detail in the future, but if anyone wants to ask any questions now, I'll be happy to take them. Otherwise, I think we are done for today. Okay, no questions? I think we're done. See everyone next time.